handout I'm sending around now is one I handed out a week or so ago that had some of the pages missing. So it's for your refreshment. I passed out the final exam also. It's a very straightforward exam. There are no tricky questions in it. The sleeper in it is that there's not any way to test yourself on some of those questions about whether they're right or wrong. It just asks for descriptions and so forth. So please be careful. That is, answer the question that's asked accurately. And none of the answers are lengthy, but you need to have the right information in it. I'd like them exams by 5 o'clock Friday night, a week from tomorrow. And you can just put them in my box in Walker Hall. Well, today I'd like to talk about sediment transport modeling. I should put up there cohesive sediment transport modeling, because that's all we'll be talking about. I've alluded to using models a number of times during the course and pointed out, gave you some slides showing some of the results of the first model. And I passed out last hour a paper that was written in the 1970s. It was the first two-dimensional model of sediment transport. I might say that prior to that time, Nicholas Odd and Michael Owen at Wallingford Hydraulics Research Station in England had used the same relations for a one-dimensional model. They revised that model to two one-dimensional models one on top of the other for the Thames, and it was used for designing what they call the barrage, the dam, and protection works against floods, tidal flooding. Then Ranjan Aryathuriai, a student here, devised the model that you saw in the handout for his doctoral thesis. And that model has been refined some, but it's the one that's used nationwide by the Corps of Engineers in their TABS 2 system. I don't recall what TABS is the acronym for, but it's essentially that model plus the RMA-2V model, hydraulic model, and input and output programs to go with the whole system. They've put that up almost in a popular version. That is, it's distributed to all the districts in the Corps of Engineers, and they give classes on its application and use. 5 years ago, the last time I heard it, it had more than 100 applications. So it is a pretty useful model. It still has limitations, and of course we'd like to have a three-dimensional models. What I'm going to talk about this morning is just the sediment transport part, not the hydraulics part. But I think you'll see where the hydraulics part fits in pretty clearly in our discussion. We use the advection diffusion point equation. And I'll put it up in 2 dimensions, let's say, where the change in concentration with respect to time plus the advection term, which is u dc dx, plus, let's say, v dc dy is equal to the diffusion terms, which is the change with respect to x of a diffusion in the x direction, dc dx, plus the change with respect to y, d in the diffusion in the y direction, dc dy, plus sources and sinks, all plus sources and sinks, and I'll discuss this more in a minute. This term, if we were doing it in 3 dimensions, there would just be a z dc dz here, and there would be a partial with respect to z of dz dc dz in this point. This term is the advection term. It's the transport of the bulk material. And this this term is a diffusion term. That's a term that takes care of the mixing processes during the flow. And then the source and sink term is a material eroded from the bed, which adds to the bottom material, or material dumped in from a barge, or material that comes in from a river. That would be a source, or deposition would be a sink. You follow me? I want to emphasize this is simply a description of the transport at a point. So if we're going to describe it in a system, we have to have additional information, and that is initial conditions, I'm writing it in capital letters because it's so important. The initial concentration of this is in terms of concentration of suspended material. So we need to know the concentration of suspended material throughout the system that we're going to model. And then the boundary conditions. And the boundary conditions are the sediment inflows from streams, or the sediment discharges to the ocean, or sediment eroded from the shores, brought in from sloughs and so forth. So we need to know all of these things before we can attempt to find a solution to this equation. This is really just a mass balance equation. That's an equal sign there. I want to point out some of the important parts of this equation. First of all, you notice it requires the velocities and the velocity and the concentration gradient, but it requires the velocities, and that means that you have to have accurate velocities at every point in the system, or if you're discretizing it, as turns out that we do, at sufficient number of points in the system so that you have a U and V known accurately. This is a term that gives you difficulty in the numerical solution, so you want to know those. You want those tied down pretty well. There are several ways of getting U's and V's that have been used. One is to go out in the estuary and measure it. Well, that's great as long as what you're modeling is what exists now. But if you want to represent some other condition, which is usually the reason for preparing a model, then you need to know the U and V for that other condition. The Waterways Experiment Station has successfully used physical models to get U and V. Recall when we walked around the physical model a couple of weeks ago, I pointed out that the physical model is truly a three-dimensional representation of the system. It doesn't have wind effects, but as far as the tidal effects are concerned, it gives a good three-dimensional representation. So you can measure U and V at a number of points in the physical model and use it in this relation. The difficulty is that the physical model is small, so you can't measure at points very close together very well. So typically what's done is to prepare a grid, whatever grid you're going to use in your solution technique, on the model, and then use some kind of a cubic spline fit or whatever kind of interpolation that appeals to you for the points in between the points that you measure, so as to fill in all the points on the grid. Well, that's been pretty successfully used on the mouth of the Columbia River, for example. I don't recall other applications of it, but it is a method that's used. The costs are very high because you have to have a physical model. If you have one already, that's fine, like our San Francisco Bay model. But if you had to build one, then it would be prohibitively expensive. The third way is to build a mathematical model of the tidal hydraulics. That's a good approach at the present state of the art for systems that are pretty well mixed. Three-dimensional modeling is really just emerging. There's a very good three-dimensional model of the Chesapeake Bay, and Prince William Sound, and Professor King is working on one in the San Francisco Bay. And I think that soon, given our progress and the availability of machines, that you'll be able to use three-dimensional hydraulic models. I hadn't planned to get into too much into hydraulic models today, but we may if it becomes important. So U and V come from a hydraulic model. D, the dispersion coefficient, this, I might say before we get into it, this term is hypothesized. It's not really a description of the physical processes. If we could describe points close enough together, if we could describe them a few centimeters apart throughout the system, we could probably eliminate these terms. These terms assume that the mixing processes can be described like those of molecular diffusion. That is, that they're completely random processes, and that the change in concentration, or that the transport, rather, is due to the change in concentration, the rate of change in concentration, or the gradient of concentration, that it's proportional to that gradient in concentration. So what happens when you go to apply this model is that D accumulates all the unknowns. That is, they wind up in some kind of a coefficient. And if you're not careful, it can include numerical dispersion, for example, in your computational steps. But in any case, D winds up having all the unknowns, and if you just blithely adjust it to make it fit observed data, you're liable to include things that you don't know about. So it's important, I think, to find D independently of your sediment model. And the way to do that is to use the same model to calculate the salinity concentration in an estuary, and assume that the salts are transported the same way, the sediments are transported the same way that the salts are. If you can reproduce the salinity by adjusting D, then you have at least some confidence that the dispersion coefficient is representative of the physical system. So you get D from the salinity. Then, if having that data, the dispersion coefficients and the velocities, then together with the initial conditions, then you can start a computation that shows a concentration everywhere in the system. The next problem is this source and sink term. Well, we spent practically the whole quarter talking about sources and sinks, deposition and erosion, and the processes that lead to deposition and erosion. So that these are simply dc dt terms, and we had for erosion, or for deposition, we had that was equal to minus the settling velocity times the concentration times the probability term divided by the depth. This depth, still call it D. This depth is the depth over which the material is mixed. If you're dealing with a 3D model, then you want to be careful that this D represents that bottom section. If you're dealing with a 2D horizontal model, then typically you use the entire depth there. For dc dt for erosion, if it's surface erosion, it might be 1 tau over tau critical minus 1 for tau greater than tau critical. And this is for tau less than tau critical. Which means that we have to find these tau critical, another parameter we put into our model. So far, for our two-dimensional model now, we have 6 parameters that we have to put in. Oh, I left one out. We have to put in this one and this one. The settling, there's still some problems with the settling velocity relation because of the different regimes that I described earlier. There's also a problem with the bed, and I'd like to turn to the source term here. During a tidal cycle, the material will deposit as slack water approaches, then during the strength of flow, it'll be wiped off again, be taken off again. That's bulk erosion, typically. It may leave some on the bottom that is subsequently eroded. But the big changes during a tidal cycle are deposition during slack water, and then possibly resuspension, sometimes not resuspension. In a marsh, for example, you wouldn't expect resuspension. But in a channel, you'd expect some of the material that deposits to be resuspended again. So the procedure is to break the bed into layers. Of whatever thickness your computational system can manage, and to keep track of the layers. So that if you have, let's call this 1, 2, 3, and 4. If during slack water you have these might be, say, 1 centimeter or 1/10 of a foot or some such thickness. If you have all these layers, you have to calculate some kind of increase in strength for this layer, and then these may be wiped off, and then at a later time this might be. So you need to keep track of the layers and the strength. It's a horrendous bookkeeping problem, what it boils down to. It's not a exotic thing at all. It's just a matter of keeping track. And what we assume typically is that the shear strength, I'll call this depth. I guess I better draw it differently. Depth here down into the bed, and shear strength, that it increases from whatever the value is for a new deposit linearly. And the rationale for that is those plots that you saw in your syllabus, showing that near the surface anyway it's linear, and the reason it's linear is that or nearly linear. It may break. Remember, we had some that had breaks in them. But if it's for a short time only, that is just during the slack water, then using a linear increase isn't too bad. So what will happen is that if it's an area of deposition, you may have 4 layers deposit during slack water and 3 of them wiped off. And then the next time you have another 4 layers, another layer up here, and 3 of them wiped off again, so that you actually get deposition. But during the tidal cycle, the concentration of suspended material may change widely because right at slack water it settles out. Remember those plots, graphs of Savannah Harbor sediment? At slack water, the material really fell out of suspension and then was resuspended again. So it's necessary to keep track of that. And that's that bulk erosion, if you like, during a tidal cycle. Mm-hmm.
This is back on the velocities. What is the difference between the U and the V?
Oh, good point, Jamie. I should have put that up to begin with. Let's make our coordinate system Z, X, and Y. And our velocities are U, V, and W. I'm sorry, folks, I didn't give you that to begin with. Okay, well, so you need to start out. Now let's suppose that we're working on a problem. To make it simple, let's say we have an enclosed harbor with a single entrance. We need to know the concentration of suspended solids initially, and we need to know what it is throughout our modeling schedule. We need to know initial concentration throughout the system initially, and we need to know what it is at the boundary. In a closed harbor, we have a single opening, so we need to know what it is throughout time. Okay, and that's a tough problem. In even that simple system, knowing the suspended solids concentration throughout the modeling time it's just about impossible. I've taken 2 approaches to that, and I think there are 3, but 2 that I recommend are One, if you have data on the harbor before it's modified, that if you just want to modify harbors, say it changes an entrance or something, then what you do is adjust the concentration at the entrance to some representative concentration that gives you the observed rate of deposition. And you can check while you're doing that to see that the pattern that you get from your model agrees with the pattern that is observed. Now, usually you don't have an existing model. You have to have some other. So the next best thing you can do is to look around the estuary and see if there's another harbor with a similar situation. Shallow area outside, whatever it is that's outside that would supply a source of it. Similar wind conditions and so forth. And I usually take about 3 of them and model them and see if you can reproduce their sedimentation rate and come up with a concentration of suspended solids at the entrance, you know, a constant concentration that is representative of the widely fluctuating concentrations that actually occur. That works well in marshes, and that marsh paper I passed out to you describes that approach for. And the interesting thing about doing it that way is that you come up with concentrations that are very, very easily to agree with. You know, they're about the middle, or maybe the upper, a little above the middle of what's actually observed out there. The second way is, I've had less success with, is to make a plot of the concentration against a probability scale, a log of the concentration against a probability scale from observations from samples taken at the location. And if you do that, what you find is that you get values that aren't too far off of a straight line. Then you can take, let's say this is 98%, and this is 2%. Then recalling that the high concentrations are the ones that bring the most sediment in, what I usually do is break this up into short segments with wider segments at the lower part, and then calculate the amount of deposition you'd get for each of these at their upper end, and then sum them all up. Now that's a hard way to do it, and it usually doesn't give us good results. It usually gives you results on the low side of what you're going to do. And the last way is to make a guess. And surprisingly, how often that's done. I don't recommend it. I think use all the information you can get, but this is a very weak part of the modeling effort, finding what the input is. Now let me elaborate a little bit. We talked about a simple system with one opening, an enclosure with one opening. Suppose you're dealing with an estuary with a stream coming into it. Now the stream's going to provide sediment supplies that vary widely throughout the year. In California, we have most of it in December through March, say. But in other parts of the country, it may vary quite a bit. And you have all these hydrographs coming in. How are you going to manage them? You know, how are you going to represent that in the system? Pretty hard. A way that's the Waterways Experiment Station does it is to use a system quite similar to this. That is to rank the storm inputs from the least to the most, and then take representative storms and let that take storms at the high end, say 3 or 4 different storms, and model them and say that represents the portion of time that you allocate to it here, and sum them all up. That's a kind of a simplified description of it, but that's essentially what they do. They modeled the growth of a delta at the mouth of the Atchafalaya River that way. It was a horrendous project, you know, to try to predict for 50 years what the growth of a delta will be from a sediment model using this model. And the results that they came out with are very credible. We'll see, you know, whether it turns out to be what they predicted, but it certainly looks well. So getting the boundary conditions, that is the inputs to the system, is difficult. I might mention another one, and that's San Francisco Bay, the loss to the ocean. You know, that's a boundary condition. How much sediment is lost to the ocean? That's a difficult problem. What we're doing now, and I've done in the past, is to make a sediment balance. Take the hydrographic surveys of the system. I think I described that to you with some slides, recall. Make hydrographic surveys at different times, calculate the accumulation of sediment in the system, then from the river inflows and the suspended solids concentration in the rivers, calculate the total amount of sediment that came into the system during that time, and then calculate the amount of that goes out through the Golden Gate by difference. The problem there is that you have to do it over a year's time. That is, because of the seasonality of the system, there's no way you can really break that up into transient times without having a model to model that whole thing. Well, we aren't yet able to afford modeling a year, and the system is complicated as San Francisco Bay. That is actually going through a whole year's model. So what you do is break it up into pieces, and then say this piece represents so much of the year and so on, based on some kind of a probability distribution. That's an area that desperately needs research. We need some better way to synthesize from a few computations what the whole picture looks like for sediment. I think that's done. Hydrologists do it to some extent for runoff, but there's still a lot of room for improvement in sediment. The initial condition problem is one that is usually gotten around by finessing. What you do is select some initial condition. Let's say uniform concentration throughout the system at some intermediate value. And then run the model for a while, a warm, so to speak, until some kind of a distribution, and use that as your initial condition. That's probably not too bad. You know, it's not too bad an approach for modeling, but it takes a lot of computational time. So, see, there are a couple other points I wanted to... Oh yeah, the last one is the settling velocity. The difficulty is that we aren't really able to get settling velocities in a reliable way. The way that we've been talking about using by some constant times the concentration of 4/3 power works pretty well in systems where the breakup isn't a process. That is, where aggregates have formed to the point where repeated collisions are infrequent. And that might be a case in let's say, in marshland. And it's probably not too bad say, in an enclosed harbor, where the breakup is not a breakup of the aggregates by the high velocity gradients near the bed is not a significant factor. But out in channels where the velocity gradients are pretty high near the bed, then you get breakup, and the settling velocity is not a simple function of concentration like that. It changes with the velocity gradient. Probably Shrestha, one of your associates, has found that he can use this relationship for W sub s, provided that he adjusts K as a function of the velocity gradient, of the average velocity gradient in the system. And he used for his average velocity gradient the, I'll call it G for an average velocity gradient, equal to the power dissipation divided by the viscosity, the 1/2 power square root. And he said that K is some function of G. He actually used W sub s equals K of G times C, which is N, also depending on G. But if you look at his N's, they're all about 4/3. So I'm not so sure that's too important. But having this K change as a function of the energy dissipation seems reasonable. Well, the power dissipation or energy dissipation per unit volume can be gotten in several ways. One is this G average would be rho U star cubed over eta times some depth, where 1/2. There's several ways you can get at it, but then what you need to do is to obtain some of the material and determine this function of G, this K of G. He determined it from settling tests, from settling in a vertical cylinder with a paddle in it. And the paddle gave a torque, and from the torque then you can calculate the power to energy dissipation per unit volume, and he allowed them to settle. He took some other people's data to do that.
Is there any way that assessing the actual states of aggregation in that sample that was tested?
Well, what's usually done is to model the existing system and adjust K to fit, or adjust W sub S to fit, and then hope that it stays the same when you modify the system. And you can generally tell. If you haven't changed the velocity gradients a lot, then it probably won't be too much different. But the real weaknesses in this model are, first of all, getting reliable U and V, and then D you can get pretty well from the salinity, and then getting W sub S. Those are the weakest parts of the model. I don't think I'll spend any time on solution techniques. That's really not my field. Professor King and Professor Herman and Professor LaRock are all specialized in that area. But the usual procedure is to discretize it and use either one of the finite difference methods or a finite element method. And there aren't analytic solutions to this, really. I'll have to say something else about modeling while we're on it, because models are a little too easily accepted, in my view. You'll find that consulting firms will take somebody's model and put it on their machine and put all the information that the model demands into it and accept the results. The critical thing about modeling is visualizing the system, that is, knowing pretty well what the system is, understanding what the processes are, and then exercising the model. And it's a good idea to know what's in the model. That is to look at the source code and see exactly what's been done, because there are often some shortcuts in it. Then exercise the model using known inputs and known and expected outputs, that is, verify the model. Only after you're satisfied that the model truly represents the system that you're dealing with, try the changes, and then you're essentially extrapolating from an existing system. Last summer, the Committee on Tidal Hydraulics was asked to review an application for a new harbor facility at Anchorage, Alaska. And we were given modeled data from a company up there that had modeled this new harbor, and the intent of the modeling was to show that there was no impact on adjacent harbors. No, it wouldn't cause more rapid sedimentation in adjacent harbors. And the model report was about that thick, It was quite an effort on behalf of the people, but the modelers didn't understand the system. There were horrible gaps in it, and the results were not credible at all because of the actual gaps in it. One of the things they did was, in order to get the model to run on their system, on their hardware, they left out some of the terms, the acceleration terms in the hydraulic model, for example. In a system with a 10-meter tide, accelerations are pretty important in that system. And they came out with a beautiful report that did just what you'd expect it to. All the currents went in nice geometric ways, and it was a real impressive lesson in how not to go about modeling. And I think even people with a lot of experience will want to exercise the model that they develop enough so that they're confident that it is truly representing the system. The way you build that confidence is, as far as possible, get all of your inputs independent from your model. That is, minimize the number of things that you adjust to make the model fit the system. Get the settling velocities, if you can, independently, and of course, the currents, and the diffusion coefficients. Make sure they represent the salinities, and then compare the values that you get to similar models, if you can. You'll find that sometimes you get outrageous numbers. If you just try to make the model fit observed data, you get outrageous numbers. That's a warning that there's something wrong in the model. There's some uncertainty that's being included in your diffusion coefficient. Well, in spite of all those cautions, models are very useful tools. They give you quantitative information on the deposition rates or erosion rates, and sometimes they're the only solution to a problem. And I'd like to just describe a couple of problems before I leave this subject, where you couldn't very well do it without models, but more importantly, that they illustrate methods of applying them. Down in Argentina, there's a bridge across the Paraná River called the Brazos Largos Bridge. I don't know if any of you are from Argentina. It's about the size of the San Francisco-Oakland Bay Bridge. And it was built by putting, filling in landfills like the approach to the Oakland Bridge on both sides of the river. So it actually constricted the flow of the river. And the caissons went down into cohesive material, it was actually pretty strong material. It was compacted soils. And the issue was, how deep did the caissons have to go? Well, as you can imagine, every meter has increased the cost considerably. So they didn't want to put them any deeper than they had to, but they wanted to be at least deep enough so that the bridge would stay, and that the increase in currents resulting from the narrow channel wouldn't scour them out. The main cause of bridge failure is scour of the foundation. So we approached the model. This was 1975, where modeling wasn't nearly as advanced as it is now. But the approach, I think, would be the same. We approached this problem by, first of all, constructing a model of the flows around the pylon. Secondly, we had samples of the mud flown up, and we used that rotating cylinder apparatus I described to determine the critical shear strength for erosion of the mud. And that gave us a boundary, it would erode until the bed shear stress equaled the shear strength of that material. You can put a safety factor on top of that, but essentially that was the method. And then having this model, we needed some way to verify it. It was a pretty crude model. It was a stream flow model. We essentially divided the flow into vertical slices, and the flow went around the caissons. So we set up a hydraulic lab at Rosario. It's a university lab about 200 kilometers from Buenos Aires, and put in a small caisson model, and first of all, made a bed of this cohesive material as undisturbed as we could. We took squares and put it in there, and put this caisson in it, and it was only about that big in this flume, and the flume was about that wide. And then turned the water on and let it erode, and we kept measuring the depth of erosion until it didn't erode any deeper. Then we modeled that with our numerical model. We modeled that system at that scale with the numerical model to give us some assurance that the model was actually represented a physical system. Now, there's a lot of scaling laws involved and so on, but we didn't use this flume as a model of the final system. We used it as a system itself that could be used to verify the model. So we modeled that flume system with a numerical model, and it gave good, reliable, accurate results. So then we modeled the full-scale thing using the mathematical model, and came out that it had to be 15 meters deep, if I remember correctly. Well, the bridge was built, and it's been standing now for 10 or 11 years, so far, so good. But the point I wanted to make was that sometimes there isn't a way to go out and calibrate your model or verify it. And to do that, you can use smaller scale or slightly different system to represent it. Another example I'll give you.
When you said they had pulled up this mud sample, how deep did they go for those samples? Did you have different samples from different levels
From
of
the,
mud that they pull up from Argentina?
how far?
How far down did they?
Oh, the samples they took? They took samples of various depths, and we asked for undisturbed samples. Well, of course, sample isn't really undisturbed, but as undisturbed as we could get. And they took it from a number of depths, and air mailed them up, just flew them up. And we used that rotating cylinder apparatus. It's a convenient method and suitable for that kind of thing. We've done that on a number of foundation problems. Well, one other project I want to illustrate, and that is a mud flow study that was done by Vita Wright here. Mud flows are, Dr. MacArthur showed you some pictures of mud flows. There's no way of predicting when they're going to happen, or almost where they're going to happen. You can say where they might happen, but you can't really say where it's going to happen. And so getting instruments out and getting real data is just about impossible. You spend your lifetime going around instrumenting mountainsides and hoping to get some data sooner or later that you can use to verify a model. So we set up the flume, and you can still see the apparatus over in 105 Walker with it's a tilting flume, and we put a lucite box up at the end that could be filled with mud having various concentrations. And then it had like a guillotine gate in it that could be lifted in, I think it was 0.2 of a second. So that you suddenly had a wall of mud that could flow down the channel. And we used automatic cameras to measure the shape of the progressing front as it went down the channel. And we had markers, scales on the side of the flume and markers in the top. And there's a camera above and 2 cameras from the side. And from those you could get the speed and the depth of the advancing front. It took about 4 seconds for the mud to slosh down to the far end. It made a mess. But it gave you simultaneously the shape and the velocity of the advancing front. And then we used a one-dimensional model to model that with a simplified Bingham we assumed that a velocity profile would look something like this. That is a 2-part profile with a plug flow. This is the top. Plug flow in part of it, and then a velocity gradient in the lower part. And for lack of better information, we assumed this to be a linear profile. We haven't yet found any way to measure the velocities in mud reliably. So not having anything but the external velocities top. And it appeared that it was plug flow. That is, anything put on the top just stayed on the top, and the top shape of the top change very much. And using this kind of a velocity profile, we calculated this depth here, I'll call it delta, as a function of distance from the model. And the model represented it very well. Represented as good as could be, even with that simplified profile. So we verified the model on the flume study. Then we can take that model and go out and say, we expect that a full-scale one will work the same way. Now there's a little bit of leap in faith there, but at least you have verified it in a system that you can deal with and instrument and repeat. We did it with many concentrations and with different slopes, and tested the model over the ranges of concentration and slope. Well, I plan to save the last 15 minutes for questions, and I've run over a little bit, but do you have any questions?
Yeah. How to decide erosion rate? I think that's the most difficult part. Erosion rate, just like erosion rate.
Oh, this one?
Yeah,
M?
Yeah.
M, this is for surface erosion. I described the layer by layer for bulk erosion. For surface erosion, the only way you can get that is by laboratory measurement.
And so,
From a rotating cylinder or from
so what's the range it could be tested by a rotating instrument? I mean, what's the concentration limitation for that experiment?
the rotating cylinder.
Yeah, I guess it should be high.
Yeah.
Probably over several hundred.
Haven't I described the rotating cylinder apparatus? I thought I did.
Not in
It's you take a cylinder of mud, take a core sample, and keep it in its jacket until you're ready to use it. Make sure it's saturated, and if it was wet to begin with, it's been kept wet. And while it's still in the jacket, you drill a hole in it, and put it on a mandrel that we have down there that simply puts a plate on the bottom. I got that wrong. On the top, so that you have mud held on a rod like this. The sample's held on the rod with exposed mud surface on the outside. And you insert that in a rotating cylinder, mounted on a shaft that can be rotated at different speeds, omega, let's say, and fill the annular space with water. Here. And fill this space in here with water. Then, and this is mounted on, let's say, some kind of a mount. Then the technique is to rotate this outer cylinder at a given speed for, say, 1 minute, and then lift this out and weigh it, and then put it back in and rotate this again for a minute, and do that repeatedly until you can plot the loss in weight. I'll call it E dot, loss in weight per meter of surface, as a function of oh, I forgot something. We have the shear stress on the surface here. The shear stress on this surface is some function of omega, which we determine by measurement on the inner cylinder, actually measuring this force on the inner cylinder. So we can plot this as a function of shear stress. And what we find is that at low shear stresses, this is 0, there isn't any erosion. That is, at very low shear stresses, there's very little erosion. But at some, if you keep it increasing the shear stress, then there begins to be erosion at some rate. No, I've got this wrong. Yeah, we plot weight loss. That's what I said we measure here. And each of these is for a minute so that we can you find that there is some rate of erosion, which is this is E dot, with an intercept here. Now, if we increase omega so that there's greater shear stress, I'm sorry, this is for each, I didn't say that very well. For low RPM, we get low values, and at some RPM, we finally begin to get values. With, that's still not right. That's still not right. Let me start again. We have weight loss, and we have time. Okay. And at low RPM, nothing happens. So we just get values along here with each succeeding value. At an increasing RPM, we begin to get values. I'm sorry, folks. And this is 0. And if we increase it still further, we get higher values and higher values. And for each one of these, we have an erosion rate. The slope is an erosion rate. Then we can plot the erosion rate against, and this is omega 1, omega 2, omega 0, call it, and so on. And for each omega, we have a shear stress. And if we plot erosion rate, the slope of this, against the shear stress, then we find that we have low values, and then we get a value like this. And this is tau critical for erosion, and the slope of this is your M. I thought I described this during the course.
What solid concentration should these samples have?
What?
Solid concentration. I think if the concentration is low, the sample could not be held at place, I guess.
Oh, if they're not cohesive, it won't work. If they won't.
I mean, what density the samples should have? Density of the samples.
Solid concentration.
Solid concentration of the samples.
The soil
Solid.
concentration? Well, it depends on its cohesiveness. You know, it has to stay within this. You can have a fairly low concentration if it's very cohesive. But if it's not sufficiently dense and strong to stay in that mandrel, this won't work. Then you have to use a flume.
Yeah.
You have to use a flume.
Is there anybody who try to calculate the erosion rate?
From
Yeah. I mean, if there is
in the flume, you mean?
somebody who try to calculate the erosion rate.
Erosion rate?
Yeah.
From what? From what information? From what information?
Yeah. I mean, is there anybody who try to do that?
The calculations have to start somewhere. You have to have some information to put into it. Yeah.
I think he means from mineral properties or just from the...
Yeah.
Okay. Well, I described using cation exchange capacity for estimating. Remember that? That's just a correlation. It's not based on anything other than observing shear strength and measuring cation exchange capacity. It's only one I know. There's been, well, I take it back. There's been there is erosion used in the universal soil loss equation that's based on sand, silt, and clay content. Are you familiar with that? It's not very applicable for this kind of thing. You have a question?
Have you ever seen that map in the Water Resources Center archive? It's a map of San Francisco Bay, and it has little dots to represent the pollution concentrations throughout the bay. You know what I'm talking about? Well, what I wanted to ask you about is one of the areas of highest concentration was right in the Carquinez Straits as a result of the Chevron plant.
Mm-hmm.
And I was thinking that's the mixing zone. And are there implications to related to the fact that they're dumping in the mixing zone, and is it better or worse from a standpoint of absorption by cohesive sediment in that area?
It is a bad place to have it. First of all, it's a migratory pathway for all the fish that migrate up into the Central Valley. And so they're forced to pass through that zone. It's not only Chevron, but if you go up the Carquinez Straits, there's heavy industry all the way up to Chips Island, and most of them discharge into Carquinez Straits. You know, up until about 1960, Pittsburgh took its water supply out of that area. Yeah, but the salmon fishery is just about dead, and the striped bass fishery is almost gone.
If they were to all discharge maybe on the ocean side of the mixing zone, would it
Well, the problem is that it's not just the waste discharges, it's also the fact that the freshwater outflow has been reduced to the point where the mixing zone now has moved way up into the system, and there's much less ocean water diluting it. So the residence time has increased. That is, the time that the water stays in a region has increased a lot. And if you have continuing waste discharge into that, it means that the ambient concentration gets higher. So the problem is a combination of less freshwater outflow and increased waste discharges. And of course, as this Pittsburgh and Antioch and Martinez and Benicia have grown in size, they also put waste out in there. But yeah, it's a sad, very sad situation. So, and it's one that, well, the Department of Water Resources needs to be very aware of. They're the ones that, you know, are contributing to that low freshwater output. Any other questions? General questions that you might have about the course?
This rotating cylinder test, the characteristics of the water, and so they affect the shear stress of the soil.
That's right. If you put in, typically when you use that apparatus, you take water from the system, the actual system that you're going to use, and use that water. But if you make up a soil sample, say Mount Marilonite sample, you consolidate it so that it's, you know, firm and will stand in this apparatus, and you put salt water in it, you'll find that you go almost to the limit of the apparatus' ability to provide shear stress before anything happens at all. If you put distilled water in it at about 20 dynes per square centimeter, it all starts to come apart. And so that's absolutely right. The composition of the water is very important.
So if you've got large freshwater flows, and you're going to have dilution plus high velocities with that combination, would you want to worry about that when you're modeling this?
You're talking about the Carquinez Straits? Or?
Carquinez Straits or any estuary that has freshwater flows
Oh,
coming into it. At high
yeah. Then you'd want to test it with the most, where it's most susceptible.
It would seem by using this technique of weighing the soil to determine how much soil is lost, you're also weighing some water, or not?
The water in the soil.
Entrain water in the soil, and as you lose more soil, you're also losing the ability to entrain more water. So I would think that a process of actually measuring the sediment concentration the change in concentration to the water would be a more accurate way than weighing the difference in weight from the sample itself.
You can calculate it from either the concentration or the other, but you have to know what the moisture content of the sample is. If you know the moisture content, you can calculate the solids loss. Well, folks, we came to the last minute of the last lecture. I've enjoyed this course very much, and this is my last lecture too. I plan to teach some more short courses. I've been doing that over the years for the Army and others, but no more quarter-long classes. Yeah. I really want you to do well on the final, and I suggested in the introduction there that you read the questions, study if you need to, you know, look at your notes, and then do the exam all at once. You can go back to your notes if you need to during the exam, but I found, and I think you probably found too during your years in school, that each question sort of warms you up for the next one. So you generally do better if you do answer all the questions at one time. Have them in my box by Friday at 5 o'clock. Thanks.